Section 3 of Chapter 10, Dynamics of Rotational Motion, Moments of Inertia. Let's return to the example of a mass attached to a spring and traveling around a circle on a frictionless table, shown in Figure 1011 here. In addition to gravity and the normal force from the table, which are not drawn in the picture, there are two other forces on the mass. Looking at it from above, we see that there is a tension in the string, which makes it travel in a circular path. These are all the forces that are necessary for the mass to travel around the circle at a constant speed. Note, it does not have a constant velocity, but it does have a constant speed if the force labeled F were not there. If we want the mass to speed up, we apply the force labeled F to it in a direction that is always perpendicular to the tension. Let's freeze this picture at some point in time. At this point, as at any other point in the motion, the force F is perpendicular to the string and the tension is along the string. The force F will produce an acceleration in the direction the mass is traveling, given by Newton's second law. This acceleration is called the tangential acceleration because it is in a direction that is tangent to the circular path. That acceleration is equal to r times alpha. If we take this equation and multiply it by r, we get Rf equals mr squared times alpha. The left-hand side, Rf, is torque, and the right-hand side is I alpha, if we replace mr squared with I. This is what we call moment of inertia. So, for rotational dynamics, Newton's second law, F equals ma, becomes torque equals I alpha. In linear or translational dynamics, mass is a measure of how difficult it is to change the velocity of an object. In rotational dynamics, moment of inertia I is a measure of how difficult it is to change the angular velocity of an object. Note that it depends not only on how much mass something has, but also on how it is distributed. Now, we've identified the moment of inertia of a point mass as mr squared. How do we get moments of inertia for objects that are not point masses? For any object, I can imagine breaking it up into small pieces and treat each individual piece as a point mass. I then add up the moments of inertia of all the individual pieces to get the total moment of inertia for the object. Let's take a look at a ring or a hoop. For this object, we can break it into small pieces, but each piece is at the same distance from the center. When we add up all the little mr squareds, they all have the same r's, so we just get the total mass times r squared. Let's take a look at a disk. For the disk, if we break it up into a bunch of small masses, the masses will be at different distances from the center. So it would take a little calculus to show that the moment of inertia for a disk is 1/2 mr squared. Figure 1012 shows the moments of inertia for a few common shapes. Now that we have Newton's law in rotational form, torque equals I alpha, and we have I for certain shapes, let's take a look at an example problem. A 2-meter long string is wrapped around a 20-centimeter diameter, 5-kilogram disc. The disc is free to rotate about an axis at its center. A constant force of 4 newtons is applied to the string. The disc starts from rest. Part A. Calculate the angular acceleration alpha of the disc. B. Calculate how long it takes for the end of the string to reach point A. C. Calculate how fast the disk is rotating when the end of the string reaches point A. I solved part C using rotational kinematics equations, but it can also be solved using the work energy theorem if we know what the kinetic energy of a rotating object is. We will cover this in the next section.